Hi, everybody. If you want the temperature reading passage read to you, then listen up. You probably put on a sweater or a jacket when it's cold. Likewise, you probably wear shorts in the summer when it gets hot. But how hot is hot and how cold is cold? Think about the knobs on a water faucet. They are labeled H for hot and C for cold. But does only hot water come out when the hot water knob is on? You may have noticed that when you first turn on the hot water, the water is warm or even cool. Is the label on the knob wrong? The terms hot and cold are not scientific terms. If you really want to specify how hot or cold something is, you must use temperature. What is temperature? You probably think of temperature as a measure of how hot or cold something is, but using the terms hot and cold can be confusing. Imagine that you are outside on a hot day. You step onto a shady porch where a fan is blowing. You think it feels cool there. Then your friend comes out onto the porch from an air-conditioned house. She thinks it feels warm. Using the word temperature instead of words such as cool or warm avoids confusion. Scientifically, temperature is a measure of the average kinetic energy of the particles in an object. Temperature and kinetic energy. All matter is made of atoms or molecules that are always moving, even if it doesn't look like they are. Because the particles are in motion, they have kinetic energy. The faster the particles are moving, the more kinetic energy they have. Look at figure 1. The more kinetic energy the particles of an object have, the higher the temperature of an object is. Particles of matter are always moving, but they move in different directions and at different speeds. The motion of particles is random. Because particles are moving at different speeds, individual particles have different amounts of kinetic energy. But the average kinetic energy of all of the particles in an object can be measured. When you measure an object's temperature, you measure the average kinetic energy of all of the particles in the object. The temperature of a substance depends on the average kinetic energy of all of its particles. Its temperature does not depend on how much of it you have. Look at figure 2. A pot of tea and a cup of tea each have a different amount of tea, but their atoms have the same average kinetic energy. So the pot of tea and the cup of tea are the same temperature. Measuring temperature. How would you measure the temperature of a steaming cup of hot chocolate? Would you take a sip of it or stick your finger in it? You probably would not. You would use a thermometer. Using a thermometer. Many thermometers are thin glass tubes filled with a liquid. Mercury and alcohol are often used in thermometers because they remain in liquid form over a large temperature range. Thermometers can measure temperature because of a property called thermal expansion. Thermal expansion is the increase in the volume of a substance because of an increase in temperature. As a substance's temperature increases, its particles move faster and spread out. So, there is more space between them and the substance expands. Mercury and alcohol expand by constant amounts for a given change in temperature. Look at the thermometers in figure 3. They are all at the same temperature. So the alcohol in each thermometer has expanded the same amount. But the number for each thermometer is different because a different temperature scale is marked on each one. Temperature scales. Look at figure 4. When a weather report is given, you will probably hear the temperature given in degrees Fahrenheit. Scientists, however, often use the Celsius scale. In the Celsius scale, the temperature range between the freezing point and boiling point of water is divided into 100 equal parts called degrees Celsius. A third scale, the Kelvin or absolute scale, is the official SI temperature scale. The Kelvin scale is divided into units called kelvins, not degrees Kelvin. The lowest temperature on the Kelvin scale is 0 Kelvin, which is called absolute zero. Absolute zero, about negative 459 degrees Fahrenheit, is the temperature at which all molecular motion stops. It is not possible to actually reach absolute zero, although temperatures very close to 0 Kelvin have been reached in laboratories. Temperature conversion. As shown by the thermometers on the previous page, a given temperature is represented by different numbers on the 3 temperature scales. For example, the freezing point of water is 32 degrees Fahrenheit, 0 degrees Kelvin, 0 degrees Celsius, or 273 Kelvin. The temperature 0 degrees Celsius is actually much higher than 0 Kelvin, but a change of 1 Kelvin is equal to a change of 1 Celsius degree. The temperature 0 degrees Celsius is higher than 0 degrees Fahrenheit, but a change of 1 Fahrenheit degree is not equal to a change of 1 Celsius degree. You can convert from one scale to another using the equations shown in Table 1 below. More about thermal expansion. You have learned about how thermal expansion works in the liquids that fill thermometers. Thermal expansion has many other applications. Below you will read about a case in which thermal expansion can be dangerous, one in which it can be useful, and one in which it can carry you into the air. Expansion joints on highways. Have you ever gone across a highway bridge in a car? You probably heard and felt a thunk every couple of seconds as you went over the bridge. That sound is made when the car goes over small gaps called expansion joints shown in Figure 5. If the weather is very hot, the bridge can heat up enough to expand. As it expands, there is a danger of the bridge breaking. Expansion joints keep segments of the bridge apart so that they have room to expand without the bridge breaking. Bimetallic strips in thermostats. Thermal expansion also occurs in a thermostat, the device that controls the heater in your home. Some thermostats have a bimetallic strip inside. A bimetallic strip is made of 2 different metals stacked in a thin strip. Because different materials expand at different rates, one of the metals expands more than the other when the strip gets hot. This makes the strip coil and uncoil in response to changes in temperature. This coiling and uncoiling closes and opens an electric circuit that turns the heater on and off in your home, as shown in Figure 6. Thermal expansion in hot air balloons. You may have heard the expression hot air rises. If you have ever seen hot air balloons peacefully gliding through the sky, you have seen this principle at work. But why does hot air rise? When a gas is heated, as shown in Figure 7, its particles have more kinetic energy. They move around more quickly, so there is more space between them. The gas is then able to expand if it is not kept at the same volume by its container. When air, which is a mixture of gases, inside a hot air balloon is heated, the air expands. As it expands, it becomes less dense than the air outside the balloon. So the balloon goes up, and away.